Okay, let's say we have a laminar flow in the entrance to a pipe. As shown below, the entrance flow is uniform, and we assume that U is equal to U naught here. And then here you could see here the entrance is U naught at this one. And the flow downstream is parabolic in profile of UR equals C R naught square minus R square, as shown in this equation. So the UR here is actually the velocity distribution for this one, for the fully developed flow inside the pipe. Okay, the U here is, we assume that this is the velocity just for the fluid before entering the pipe. So we assume that this is the initial velocity. So using the integral relation, so another word for integral relation here is the integral form. Okay, you may have these notes from my website too. So because we have differential form and we have integral form. So show that the viscous drag exerted on the pipe wall between 0 and x. So this is 0 and x here is given by the drag force is equal pi r naught square, p naught minus px minus 1 over 3 rho u naught square. Okay, and then the integral form here is actually closely related to the Renault transport theorem. So the Renault transport theorem, okay, so I will explain the Renault transport theorem later on. So I think you already heard about this one. So UR is equal C R naught square minus R2 is the velocity distribution for this one. And what we need to calculate first, what we need to determine first is the value of C, because the C is actually the constant and we need to determine the value of C. Okay, so this is the idea of Renault transport theorem. So the idea is stick to the continuity equation. So it's called, we must make sure that mass flow rate at inlet must be equal to mass flow rate at the outlet. Okay, so the basic equation is showing like this one. So rho naught, A naught, U naught. So you know that M dot can be calculated by rho AV. So this is the rho at the beginning, at the initial state. A is the cross-sectional and U is the initial velocity. And then the integration here is showing the, okay, so because, so we have a pipe here, and then the velocity distribution will become like this. So, and then, so because the velocity here is different, okay, because it becomes bigger and bigger, and then it will have the highest velocity at the center line, and then it will reduce like this one. So we need to calculate this one by the idea of integration. Okay, for example, we take, okay, I'm sorry. Normally we take the, not the center. Okay, this is the velocity, and normally we take one small area here, for example. So we need to calculate what is the mass flow rate for this small area here. And then to get the total area of this velocity profile, so we need to integrate this function. This function means to integrate the function for this small area. And then please bear in mind that this is actually the circular pipe. So if we have a 3D pipe, a 3D dimension, a 3D diagram here, so this area is actually referred to this kind of area. Okay, I mean a small circular strip, a ring-shaped strip here. So at the same time, it is actually reflect at this area. Okay, so it will circle like this. So it will become a hollow, something like a hollow cylinder. Okay, I hope you could imagine it is not a it is not a square shape. It is actually a circular. Okay, so and then if we have this area, so what is the mass flow rate for this red color area? So the idea is still the same. So if the equation for the mass flow rate is m dot is equal to rho A and V, so we know rho is the density of the fluid. So okay, and A is the cross-sectional area. So, and this cross-sectional area is actually the cross-sectional area of the ring shape here. Okay, and the velocity here is the velocity for the shaded area, for the red area here. So, the velocity for this one will determine as U. Okay, and then the ring area here, you could imagine that if we have ring there, okay, if we have ring like this, okay, and then if we cut this one, for example, we cut this one, and then we could stretch this like a very thin rectangular area. So to get the area of this rectangular is to multiply the length, which is the perimeter of the ring, which is 2 pi r, with the thickness of the ring. So the thickness of the ring here is actually can be reflected as dr. So that's why we could calculate here dA means the small area, means the area of this strip is dA is 2 pi r times dr. So that's why we have a 2 pi r times dr here. And then we have u. So u is c r naught square over cr. So it is given in the question, and the rho is the initial rho of this one. So it is equal. So if we assume it is incompressible, so we could take the rho naught here as the constants. Okay, so so and then because we assume that it is incompressible flow, so we could neglect the value of density here. So this is our calculate our equation now. So we have we do the integral to dr here. So we have this one, and then the limit of the integration is from the 0 to the r. So I know you I think you already know, because we have r equal to 0 in the middle, and then we have r equal to capital R at the outside here, the maximum value of radius. So we could say that it is equal to pi c r by the power of 4 over 4 here. And if we solve this equation, we could get C is equal to u naught over r square, and then we substitute in this one, so we get the ur is equal to 2 u naught over r square, r naught square minus r2. Now we have our velocity distribution here with the constant of c. Then we need to calculate what is the drag force for the element. So the idea is we should start from the free body diagram. So for example, because the question asks us to calculate the drag force between the x-axis 0 to x here. So we just imagine that we have a circular one, the cylinder shape like this one. So this is the side view. So you see it as a rectangular shape. So and then we need to apply with the Renault transport theorem or the integral form. So you could make a revision about that. So the idea is, so the simple one, how to deal with this one is, okay, for example, we have a pipe here. So and then the flow is flowing from left to the right like this. And then now we want to evaluate only from the point of 0 to the point of x here. Okay. And then, okay, we need to create a free body diagram. So free body diagram means we try to take out the whole situation into a static condition without neglecting all the parameters that actually act on that element. So the idea is simple. So for example, if we cut this pipe, so if we cut this pipe and we don't want to, we cut that pipe, and at the same time, we must make sure that this fluid inside this section is still having their own pressure. So what we need to do is we must to make sure that we push it to this direction at the same time, because we don't want this fluid inside this area flow out. So if we cut this one and this one, so it has possibility of this fluid to flow out. And then you please imagine that to prevent the fluid to flow out like this, so what we need to do is we need to push this surface with certain force. Okay, that's why we have means that we cut this one, then to make sure that we remain the internal pressure there, so we push at certain force from the left to and from the right. So that's why we push P naught A naught here. You know, pressure times area is the force, so you need to push force here, P naught A naught, and also another force here, okay, to make sure that the situation inside this control volume is maintained there. So and then we label the direction of velocity. So in real situation, the velocity is from left to the right like this, and this is also to the left to the right. Okay, so and then we give it the vector axis. So this is the rules. So it depends. Some textbook they will give you ideas how to calculate this one by using the direction or the flow rate in inlet and outlet. But I'm going to tell you about the idea of this one. So the idea give the vector n here is from the surface here, you need to make an arrow outside like this one. Okay, this is the rule. Just okay. So to simplify this one, okay. So this is the way we create our free body diagram here. So and then finally we put the direction of drag force. So as you know that the velocity is moving from left to right, so means that the drag force means the force that acts in the reverse direction. So the drag force direction is actually from right to the left. Okay, right, this one. Okay, so now you already show all the necessary parts in this free body diagram, and to solve this one, so we need to stick with the idea of Renault transport theorem. So the idea is here dt for mv. So mv here is actually reflect the total force. The total force. And this is the force that acts on the control volume. CV here is control volume, and this is the force that acts on the control surface. Okay, so in this situation, we found that the element for the control volume is equal to 0. Okay, how to determine whether the control volume or the control surface exists or not? So it's depend on the situation, it's depend on your application. So in this application, so we have a pipe here. So and then we have a fluid flowing inside the pipe, and what we know is the velocity will flow at certain cross-section area, and it will create a flow rate, and then it will give you a different pressure might be, and so on and so forth. So means that the effect comes from the surface here, from the control surface. However, the volume or the shape of the pipe here is not changed, because this pipe is not increased like this. It's not ballooning, it's not expand itself, and also the tank, the volume of that medium is not filled by water. So for example, if you have one tank like this, so this is a closed tank, for example, but the water is start at this level. So when you have a flow rate in and flow rate out, so it is possibility to the water to goes up, means that the volume inside this system is increasing. So in this situation, so you need to take care of control volume. At the same time, you need to calculate about the changes because of you have cross-sectional area at inlet and outlet here. Okay, means that at this situation, you need to think both the control volume and the control surface. But in this situation, because we are focusing on what happened inside the pipe, so the volume of pipe is not increasing, so we could neglect the effect of the control volume here. Okay, so and then about this equation, okay, about this equation, okay, you need to remember of this one. So you have force, so or it can be d dt for mv. So to get this one, might be some textbook they will write as m mass, because mass can be fixed. So and then you have dv over dt, because dv dt is will give you f times a. So this is the equation, and we have a partial derivation here, because sometimes might be you have m dv dt plus, so you have v dm dt, because sometimes might be you have both changes. So might be you have a certain percentage change of velocity and a certain percentage changes in mass rate, dm dt. Okay. Okay, then so the equation for control volume here is the v is the velocity, rho is the density, and the v here, so this is the idea of volume. So you have rho, v, and volume. So change by time here, and then for the control surface, so you have v, rho v, dA. So actually, it is the v here. Okay, the v here is actually reflect to the vector n. So vector n means you need to stick with you need to compare the direction of the velocity with the this direction. Okay, this is not the velocity equal with this velocity. This velocity is actually velocity that give you flow rate. Because in flow rate, we know that Q is equal AV, and mass flow rate is will become rho AV. So this rho AV is actually this one. Okay, that rho AV is actually this term. So this term, it will give you the mass flow rate. And the V here is actually the velocity vector at point compare with the direction of n. Okay, so so we could neglect the value of the terms for control volume, and this is the velocity distribution. UR is equal to U over R square minus R squared here. So then we could fulfill this equation now. So so might be you could read this equation as the total force. So this is the total force, and this is both. This is the total force, and this is okay. This is the total force, and this is the total force. Also the total force, but not caused by the mass flow rate. Okay, That's the idea. Okay, so the total force here, okay, the total force here is K negative FD plus P naught A naught and minus rho X n minus Px Ax. So we could see here in our previous here. So we assume that from left to right is the positive one. So this is the positive axis. So we have FD here, which is the negative direction. So we have negative FD. P times A is the force, and this force is positive direction, but this force is negative direction. So we could write here. So we could have we have negative FD plus P naught A naught and minus Px Ax. And here, how to fill this one? Okay, so because we have inlet and outlet, this is the if we have two inlet and two outlet, so means we need to come out with 4 parameter. If we have two inlet and one outlet, so we need to come with the 3 parameters. So mean for every surface that give you changes, so you need to take into account. So because in this situation we have only two surface, so we need to calculate the inlet here and the outlet here based on this equation. Okay, we will see it. So V here, okay, V here is okay. Okay. So V here, so I will write like this one. So as you know that one of this V, one of this V is actually, we could write as Vn, means velocity according to n vector. Okay, so we have rho AV, so we know that in the inlet the area is A naught, so we have rho here, and the velocity at the inlet is equal to U. Okay, we have U here. So then the negative U here is actually showing the velocity of this one. Okay, because this direction is reversed with the vector n here, so means the value here must be negative U naught. So that's why we write here. So we have U, rho, and negative U. Okay, and then you have we have this one. So and then okay, I just simplified this one. I don't put a U with there. So and then here we have the integral, because in the outside here, so we have the distribution, the velocity at the outside here, at the outlet here, so it is equal to the distribution of this one. So that's why we stick to the idea of UR, means the equation or the relation of velocity according to the changes of R. So this is the equation of UR. So and then if you see here, so we have the rho UR and dA. So this is the density, this is the UR, and this is the A, so which reflect the m dot there. And then we have another UR here, which reflect to the velocity of vector n. So if we see this one, that we found that the velocity here, UR, is same direction with the vector n here. Then we put the sign as a positive. So and then we could solve this one. So we integrate with the limit from 0 to R. So and then we could solve this. And finally, you will get these terms. So and then we get the FD here. So and then we solve this one. So we get the final answer of the drag force is pi r square in bracket P naught minus Px minus 1 over 3 rho u square. So this is the some ideas of Renault transport theorem. So I hope you could make a revision, because this is I think I already upload notes for the Renault transport theorem in my website. So this is the last question for our tutorial 2. So tutorial 2.18. So we have a flow through a well-designed contraction or nozzle in nearly frictionless. Suppose that water at 20 degrees Celsius flows through a horizontal nozzle at a weight flow of 50 Newton per second. So if entrance and exit diameter are 8 centimeters and 3 centimeters respectively, and the exit pressure is 1 atmospheric pressure here, estimate the entrance pressure from Bernoulli equation. So in this question, they ask you to calculate the entrance pressure, but it gives condition in by using Bernoulli equation. So the hidden ideas here is it's not compressible flow. Okay, whether the fluid medium here is air or liquid, so might be it is not compressed yet. So if the density change between inlet and outlet here, you cannot use the Bernoulli equation. You need to use the compressible flow equation. So I think you already heard about the idea of isentropic flow. So you have equation for P2 over P1, T2 over T1, and T2 over T1. So you need to calculate the Mach number and so on. So that's okay. So the limit is if the velocity is around 0.3 Mach number, mean only 0.3 times the speed of sound of that medium. So if less than 0.3 Mach number, you still could use Bernoulli equation in your calculation. Okay, let's say we have a nozzle here. So this is 0.1 and this is 0.2. So we need to calculate the pressure at inlet here, okay, at 0.1. So everything is given in this diagram. So let's take the rho of water is 998. So first, it gives you 50 Newton per second. So it's called as weight flow rate, because mass flow rate, so it will give you in kilogram. Okay, but if you have Newton here, so it means the force. So, but it's reflect the weight here. So we could calculate the 50 m dot g, mean mass flow rate times gravity here. So it's equal to rho a, v, and g. And we could calculate it is equal to 1.02 meter per second. So because the question asks us to calculate this by using the Bernoulli equation, so it is okay for us to use the flow rate equation, the continuity, which is A1 V1 is equal to A2 V2. So we could substitute all the value here to find the value of velocity at outlet. So it is equal to V2 equals 7.25 meter per second. Then we could calculate the value of pressure at 0.1 by using the Bernoulli equation here. So at this one, okay, because it is depend on you. So if you take pressure at outlet here is equal to 101 kilopascal, means 101 350 pascal. So your answer here is in ABS. Okay, means in absolute velocity. So if you take P2 here as equal to 0, means okay, your answer here is quite different, but means that your answer there is in gauge pressure. Okay, so in this situation, I'm sorry. Okay, it is not equal to. Okay, it is not equal to 0. So I use 101 kilopascal here. So please take note that the answer here is actually is in bracket ABS, showing that this value is actually in absolute velocity, in absolute pressure.